Hi, my name is Andy, and I'll be presenting our work on conditional imitation learning for multi-agent games. We will be looking at how to adapt new partners in multi-agent collaboration. Multi-agent collaboration can be difficult. For example, when we want to move furniture with friends, or if two musicians want to coordinate together on playing a duet. Even just coordinating with the same partner can be difficult, but oftentimes we actually want to work with different partners. We don't just want an AI agent that can work with one user, but rather can adapt to many different users. So the goal of our work is to study the framework of coordinating with different partners. When faced with a new partner at test time, we want to adapt as quickly as possible. In other words, there's some unknown but fixed partner distribution phi, and we can think of each partner as a draw from this distribution. And the goal is to learn an ego agent that can adapt quickly to different partners from this distribution. This task is challenging because the partner policies can be very different, and there may not exist a single static ego policy that's compatible with all of the partners. So previous works have addressed different angles of this problem. In non-stationarity works, the partner may be changing their strategy based on our actions. Some methods aim to model how the partner changes, their so-called strategy dynamics. And other works even propose to use this knowledge to influence the partner towards good equilibrium. Works that more similar to this one assume that the partner is stationary, but there are many partners we would like to work with. So we must figure out their strategy and adapt to them. However, most of these works assume access to the environment or online access to partners. And this can be problematic because oftentimes we don't have access to either. For example, when it's too costly to interact with the environment or partners. Say we want to train an AI agent to play music with expert pianists. It's unrealistic to keep a diverse pool of pianists in our living room to train our AI agent against. More realistically, we only have access to demonstrations, say YouTube videos, of pairs of musicians playing duets together. And moreover, ideally, we want a framework that can avoid reward specification. Because how do we judge how good a duet has been played? It's not so obvious. And we don't want to assume access to dynamics. In our case, dynamics includes partners, which is impractical, as we've mentioned, and is easier to train. So if we can rely on learning a policy using a data set instead of exploring the environment, then we can use supervised learning methods instead of reinforcement learning methods. So all of these factors suggest that we should put our efforts into studying how to use imitation learning to coordinate with new partners. This is what we focus on in our work. We want to learn to coordinate with new partners through imitation learning, only observing static and offline data sets, for example, diverse videos of musicians playing duets, and then being able to coordinate with new partners at test time. In the standard multi-agent imitation learning setup, the trajectories are paired. We observe pairs of ego and partner agents interacting in the environment, where tau E are the ego agents and tau P are the partner agents. Then we simply learn a joint policy pi that outputs the actions of both agents. But this is unhelpful for our goal of adapting to new agents, since we've learned a static joint policy that only works with agents from our training dataset. Instead, we want to learn a conditional policy pi that takes in the state and the partner type, so that our policy behavior can adapt to the type of partner that we're paired with. So we can't just use a neural network that takes the state and outputs the joint actions. Our neural network must also take in the partner type, phi. The problem being that we don't actually know the partner type phi, so we have to also learn that in an unsupervised way. To do so, we will use the training partners in our training dataset to form a latent space over partner strategies. In this diagram, we've modeled each pair of partners as a point in this latent space phi, which we can interpret as the strategy employed by each pair of partners. So then conditioned on the strategy phi of the partner, our policy should recover the policy that was used to form the training datasets. So in our musical coordination example, Suppose that our latent strategy encoded the playing style of the musicians. Then we might interpret the strategy as the partner playing loudly or softly, or quickly or slowly. Now, when we face a new partner, we should try to infer the strategy employed by that partner, with one caveat being that since we're testing in the online setting, these interactions won't contain trajectories from tau expert, so we have to infer the latent strategy using only the tau partner trajectories. But in any case, we can figure out the latent strategy of the new partner and then run our conditional policy to output the best ego behavior for this new partner. So using the setup that we described, we can try to run the whole framework. But one practical concern with many existing multi-agent imitation learning datasets is that data may be scarce, and this can make it difficult to learn a good partner strategy space. For example, in some existing datasets, there are only 8 trajectories to train on. And this problem is made worse because we can't query the environment for more data, so we're stuck with what we have. To mitigate this issue, our work looks towards using a low-rank prior. Now, low-rank prior has been suggested in literature that, for example, the Q function of many environments are actually low rank. And moreover, the behavior of humans or AI agents trained via random seeds can also be surprisingly low rank as well. Just as a small example, suppose that the green agent wants to move from the top left corner towards the bottom right corner. Most people would probably choose the left 2 behavior shown on this slide, and not many people would choose the zigzag behavior. So even in this simple example, we can see that the behavior from our partner distribution is unlikely to be full rank. So in our work, we experiment on 4 environments, but for brevity, we will only go over the Bandit and the Overcooked environment. So in the collaborative contextual Bandit environment, the goal is to pull the same arm as our partner in order to collect the reward of that arm. But some arms give only 0 reward and others give 1 reward. So there are 10 arms in total, 1,000 states, and 16 different partners. And at each state, the reward can be different. So the training and testing partners are generated via self-play using different random initializations. We test against baselines such as meta-learning baselines, modular policy baselines that split the architecture into task and partner specific modules, multitask baselines that train a single policy against all partners, which is then being fine-tuned, and a latent strategy baseline that learns, as we mentioned before, a latent strategy space fee over partners, but does not enforce a low-rank prior. Finally, there's our method that does enforce a low-rank prior. We see that our method outperforms the baseline, suggesting that the use of a low-rank prior can be beneficial when adapting to new partners. For confirmation, we even examine the partner policy logits and try to fit a low-rank tensor to their behavior, and we see that indeed a rank of 4 fits the data very well, suggesting again that the behavior of partners trained via random seeds can indeed be low rank. Finally, we study the overcooked environment, and in this game, the 2 players are trying to make onion soup. They need to put onions in the stove, plate them, and then serve the plate. We can visualize at least 2 distinct strategies for this layout. For example, passing items across the counter or going around in circles, but there could be many more strategies. We train on the offline dataset and then use our conditional multi-agent imitation learning framework to adapt to new humans at test time. We played against 50 different humans on Prolific through a web interface. That looks something like you see here, where users would control an agent through their keyboard, and our AI agent would get actions from our servers running the models. Then after one interaction, our model would try to adapt to the human subject, and then we would play another game after adaptation. And we see that our method was able to show the largest improvement after adapting to the 50 human partners. In summary, learning to collaborate with new partners is difficult in domains with only offline data. Existing multi-agent imitation learning methods don't handle adaptation directly. To close this gap, we introduced the framework of conditional multi-agent imitation learning. Finally, multi-agent imitation learning datasets are often scarce, so in our work, we propose to use the low-rank prior to be able to learn from just a few samples. And you can check out more details about our work in this QR code below.